Och eftersom klockan är 1 eller 12 så startar vi nu. Mycket varmt välkommen till dig. Det blir en exklusiv föreläsning för dig och för publiken som sen kommer att se videon. Ja, hon är så välkommen. Så. Trevligt att du är här. Trevligt att ni är här. Idag kommer vi att ha, som vi brukar på torsdagar, en populärvetenskaplig lunchföreläsning. Onsdagar så har vi under den här terminen gjort en mer bred allmänvetenskaplig föreläsningsserie med allt ifrån materialteknik till hälsa. Torsdagar har vi presenterat olika typer av ingångar på forskningsområdet, intelligenta industriella processer. Universitetet, som jag har sagt säkert många gånger tidigare, har en mycket definierad roll i samhället. Vi ska undervisa och vi ska forska. Och som en följd av det så har vi också ett ansvar för att berätta för samhället vad vi gör, vad vi kan och vilka personer som ni har möjlighet att lyssna på för att få del av mer information om forskning. Det här huset, Vetenskapens hus, det fantastiska gamla postkontoret i Luleå som vi fick möjlighet för 3 år sedan att ta över och skapa en gemensam plattform tillsammans med Ingenjörsvetenskapsakademin och LKAB. Vi är fortfarande väldigt glada över att vi har möjlighet att använda det. Today's lecture will be in English. It is Damiano Varagnolo, och I probably pronounced his surname wrong, but you will correct me then. You are a researcher in control engineering, and you are here today to talk about the cooling of mega data centers and how that, with the help of automatic control, can be more cost-effective and sustainable. Is that right? Then you are welcome.
Hello? Perfect.
Yes.
It works. Okay. Förlåt att jag pratar engelska. Min svenska är jättedåligt. Det är bättre för dig att jag pratar engelska. Jag kan också börja här. Okay. And maybe say a little bit something about me. Okay. Thank you for coming. I'm very glad to be here. It's an honor to be invited for this type of presentations. I'm Damiano Varagnolo. I'm an assistant professor in automatic control in the group of automatic control engineering in Luleå. I'm originally from Italy, so I've got this strange accent, and I hope it doesn't sound too weird for you. But anyway, talking about science, what I'm talking about today is how to manage data centers. What are the challenges and what are the opportunities whenever dealing with these very big scale systems? And the presentation today starts with thanking some of the people with whom I cooperated. It's a list of researchers both at the university here at LTU, in SLU in Umeå, also people at SIX, the Swedish Institute for Computer Science, and friends and all the students that have helped me. And also we've got to thank the people that sponsored our research, because of course without money there's not so much things that we can do. Especially the main companies with whom we are working right now, and the main founders, the people that are the public bodies that are giving money. And I will explain little by little why they enter into play, those players, and where. The presentation is divided in basically 4 main parts. First of all, we will discuss a little bit of what is a data center, what it means, what is physically a data center. We will also discuss what is automatic control, because not always it's clear what my field is. And I hope that I will convey the intuitions about it. And then we will combine those 2 topics into what does it mean to control a data center? How can we play around with the hardware inside? And eventually draw some conclusions and tell what is going to happen, like what is likely to happen in the future. So let's start with what is a data center. If we take the definition of Google, and Google knows what are data centers, it's a facility that centralizes an organization IT operation and equipment where it stores, manages, and disseminates its data. In Luleå, we know about Facebook because it's a very big data center, and so it's something that is very important for Luleå, for the economy of Luleå. But it's not that all the data centers are as big as Luleå, Facebook one. Also, a small room where basically a company centralizes and organizes how to process the data is a data center, technically. So technically, it's not that a data center is a building dedicated to computers. Might be also just a case, okay? And of course, since we are in our society consuming and producing a lot of information, there exist data centers that are huge. This is how a data center looks like inside. It's a Dallas data center, where each one of those things is a server. So it's a unit, it's a computer basically, made in with an opportune shape. And then we've got a lot of cables that connect all the servers among themselves and with some backbone networks. Of course, we will have some cooling infrastructure, and we will have also power units that are bringing. So somehow, data centers, as the Facebook one that we think, might be very huge and big facilities with thousands of servers. And I do not know if you have ever seen a Facebook from above, but this is Facebook in Luleå. This is a car. Where is a car? No, there's no cars here, but you see basically the size. This is an entrance for a truck. It's huge. And now they're building the third one. It consumes 120 megawatts. So it's a monster, this one, okay? But they might be also smaller and might be portable. This is a very nice concept, the portable data centers, for which basically you have all the computers inside a container, and you can deploy the container wherever you want. It's very useful whenever you've got disasters. For example, if you've got a flood, and then all the IT infrastructure gets wiped away, and you need to have bigger communication capabilities for coordinating the various people that are working for rescuing the people, you might bring and deploy a small portable data center. And here it contains everything inside. But why do data centers exist? One might think, we've got computers that can communicate through internet very fastly. Why don't we kind of, instead of having a centralized facility, why don't we distribute it? Everybody at home has got a small piece of a data center. It would be kind of easier to build. Well, having a distributed data center introduces what? Delays between the various computers. If I've got my computer, so I'm here, and this is my computer, my PC, and then I do not know, there's some friend of mine that lives in Italy, and we kind of want to have a distributed data center between Italy and Luleå. We've got a lot of delays in the communications. If instead we've got all the computers that are inside the very same place, since often computers like Facebook computers, they communicate by themselves, it's much better if they are close. And of course, it's also much easier to maintain an infrastructure. If Facebook has got a lot of servers all spread around the world, if they break down, it's a mess to fix them. Last but not least, there's security. Security plays a very big role. If if I have my own data center and the people can go inside only whenever I want and who I want, I've got a higher level of security. If instead my computer as a Facebook is managed by somebody at home, that person at home can tamper the stuff. Okay, so these huge data centers will always exist eventually. How much do they consume? What is their footprint? It's very big. Maybe this number doesn't say too much, 103 gigawatts hour in 2013 in the EU. It's actually 3% of the total electrical generation in 2013. Now it's even bigger. The market is kind of huge, you can see, it's almost $20 billion in 2013, but it already increased, of course. And the amount of CO2 emissions that are associated to data centers is bigger than the one of the aviation industry. So it's huge. We don't realize it, but basically whenever we use our cell phone, using our smartphone corresponds to consume as much energy in servers that are running the various software on the background in a data center, is equivalent to the energy that is consumed by a fridge. So it's a lot. And the footprint will always also increase, and it's expected to double every few years, because we are producing and consuming much more information. If you think now at how many videos you make with respect to 10 years ago, and how many photos you take with respect to 10 years ago, how much more data are you producing and consuming? A lot. So this is basically the forecasted IP traffic growth in zettabytes per year. This gives basically an indication how much information is produced, is expected to be produced in 2018 with respect to 2013. And of course, this kind of implies that also the number of data centers from 2013 and 2018 will double. So it's a very, very, very big market. And what happens? It happens that, maybe I was missing saying it before, but whenever we use a data center, the various servers heat up, and we need to cool them down. Because of course a computer cannot run at 100 degrees. Your computer at home, whenever it's too warm, it starts cooling down. So there's a big part of the energetic consumption is associated to cooling the data centers. And what happens? It happens that we might improve the practices that we are using right now in cooling and managing the data centers and reduce their energetic consumption. Okay, and there's some people that they are experts, say that if we implement those best practices, and I will talk about a little bit about those best practices in the data center here in Europe, basically we might save an amount of energy that corresponds to 1 million households yearly. The fact is one, it's a huge market, it's a huge infrastructure. Improving it a little bit means to have huge numbers. Okay, so just improving 2% leads to huge numbers. So there are a lot of best practices. And of course, I am limited as a researcher. It's not that I know everything. I have got very limited competences. My competences are in automatic control, so I can't contribute in all the various best practices mentioned here. But what I can do is some of the best practices. Me, as a researcher in Luleå, Tekniska universitetet, I can work on optimizing their management inside the data center, and we will see how, in which sense. Optimize how to do how to design and operate the central cooling plants. Improve the humidification systems. Reduce standby losses. We will talk about this. That means turning off the servers whenever it's not needed. And improve operations in general. Now we go into the details a little bit better. But before doing that, I should explain what it means, automatic control. What does it mean? Well, the definition from Wikipedia, it's an accurate definition actually, says that automatic control is the application of mechanisms to the operation and regulation of processes, this is the important part, without continuous direct human intervention. from an ethical perspective, I am the one that is trying to remove humans from the labor market and trying to make everybody get fired. But actually, it's a very complicated subject, this one, okay? Yes, the ethics, there's ethics in what I'm doing, trying to remove humans, in the sense of trying to make humans do not do what machines can do, but rather make humans do something that is smart to do. From a practical perspective, what is automatic control? I think that an example is better to explain. If we take an airplane, and we know that there's the automatic pilot. What is the automatic pilot? The automatic pilot takes measurements, the speed, the wind, crosswinds, the weight of the plane, and it also knows. We also know that we've got to go from this place to this place, let's say. Okay, so we've got to follow this route, and these automatic control algorithms. That means software software running on some computer. What do they do? They take the measurements from the plane. They know what the trajectory should be, and they compute how to move the various flaps and how to do the motor and how to push them up. So automatic control is this kind of branch of mathematics. Is actually applied mathematics, automatic control. It's not engineering formally. That makes a transformation from sensor measurements into actuation commands. Is it clear? I hope so. Okay, then, now that we know what automatic control is, how can we do control of a data center? And here we will stay a little bit more time. Well, let's make these control perspectives by steps. Let's take the first atomic unit inside the data center, that is one single server, one computer. How does a computer work if we abstract it, if we do not kind of look at too much at how the IT works, the information technologies works, but let's see how from a cooling perspective a computer works. We have some processing unit that processes some IT loads. For example, we want to watch a video on Facebook. It means that the Facebook server, this is like a Facebook server, gets through internet a request of process some information, get some information from one hardware, process it, and send it back to the internet. Okay. So a server has got some IT loads that has got to process, some requests from the users. It consumes some electrical power, and what else? It cools down. There's something that cools it down. There's a fan, typically, that makes the air go through the server. Of course, electrical units, they consume more power whenever the number of IT loads is higher. So the more the computer is used, the more it warms up, and the more we need to cool it down. And notice that, of course, electrical power is used both by the processor and by the fan. This is the important thing, because this one is something that we serve in any case. This one, we need to do not overcool, in the sense we do not have to use it more than necessary. And here is where we can play automatic control algorithms in a way of saving energy. From a control perspective, from a mathematical perspective, what is the control problem on a single server? The aim that we have is to maximize the quality of service. That means we do not want the people that clicked for the video have to wait for the video. Yeah, we are like a very impatient society right now. So if we click, it must be happening right now. So this one must be guaranteed. Also because if Facebook gets slower, the people will not use Facebook anymore, and then they lose money. Okay, so this is something that we can't play with. But also at the same time, we want to guarantee the quality of service, but minimize the electric consumptions. Single server, later we will make it a little bit more complicated. Anyway, what are the inputs? What are the stuff that we can manage from the engineering point of view? We can make the computer go faster or slower, because the various CPUs, they can be, there's this frequency hopping. I do not want to enter into details, but you can artificially make the computer slower, and by making it slower, it consumes less energy, okay? There's another very IT thing, that is the number of virtual machines, that is somehow how to move, how many atomic units of computation you can run inside your computer. Okay, your computers now, I do not know if you heard, but there's like this multi-processor stuff. You can think at virtual machines how many processors you are using. Of course, if you shut down some of the processors, you save energy because some part is not used. And then, of course, we can play with the fan speed. Because we can turn it on, make it faster or slower. And there's something that we can't control on a single server level. That is the IT load. The server gets a certain request, we have to process it. And there are also some disturbances, some other stuff that we can't control. For example, the temperature of the air inlet. And we've got to take into account that. And there are some dynamics behind this framework that we are saying, in the sense that, and it's important to get the hint on those dynamics. We need to guarantee the quality of service. To have the quality of service that increases, is better to increase the CPU, the frequency of the CPU, how fast the computer is. Because the faster the computer is, the better we can serve loads. But of course, if we increase the CPU frequency, what happens? We increase also the temperature. And this implies that we can break the stuff more often. At the same time, we also increase the electric consumption, because the faster the computer is, the more energy it runs. But also, if the temperature is higher, we also have to use more fans. So also this is a way of consuming more energy. And at the same time, to complicate the stuff even more, is that if we've got a higher temperature, there are some tunneling effects that I do not want to enter into details. Basically, the higher the temperature, the more the electrons inside the CPU can jump between various pieces. That means that we've got some currents, leakage currents, that are increased with the temperature, that increase the electric consumption. To make it short, the faster we make the computer, the more we consume electricity. And we consume more electricity through 3 different mechanisms. And whenever we have to regulate this stuff here, whenever we've got to regulate the fans to control the temperature, we need to take into account the fact that we have different branches. I do not want to enter into details, but I want to give you somehow the intuition of what are the problems, what are the things that we as control engineers have to think about it. Okay. And then, from a single server, this is, without formulas, the control problem. Let's go up in the hierarchy, and let's talk about the control perspectives on the server's rack. What we want to do is to keep everything cold and kind of use the fans the least that we can to maintain the temperature. But it's not that we have only one server. Often we've got racks of servers that are kind of cages. Imagine a closet full of servers, and the closet might have also its own ventilation system. So there's the local ventilation systems inside the servers, and there's the rack, the closet ventilation system. Okay, so at this point, what do we have as a system? We have all the single servers with the problems that we were having before, but now we have also kind of to take into account whenever we need to decide how to manage the fans, we need to take into account also the fact that there's air that is going around this server. So there's stuff that affects each other. If we see it, the control perspective is basically this one. We've got the same problem of before, that maximizing the quality of serving while minimizing the electric consumptions. But now we have more things that we can play on whenever we consider the whole rack. We can consider the speed, the fan speed of the rack. We can turn on and off various computers. We have also the nice stuff that we can theoretically think that if this server is overloaded and this server instead is very little loaded, we might move some IT loads from this server to this server, so to balance their consumption somehow. And there's other disturbances. But maybe this is not so interesting to say. I think that the most interesting thing to see is this one. Is the control perspectives on the whole data center. A whole data center looks typically like this one. We have a lot of closets, and we have typically two zones. One that is called the cold zone, where we've got cold air, and the cold air goes through the racks, gets warmer, and then this warm air here is treated as an exhaust, and we take it away. And then the control problem, what is the control problem? Understand what is the temperature of this cold air that guarantees the various racks to be cooled enough. How fast the air should move. How we should make the various single servers work with their local fans. How the single racks with their fans should work. And how to make everything work all together in a way that this cold air is the warmest possible. And this stuff here turns the least possible. Because this is somehow the stuff that drives the energy consumption, the centralized system. And now, you might think, do we want this warm air the coldest possible, or would we like this to be the warmest possible? The answer is the warmest possible. The fact is this one, and this is the main message that I want to give. Those monsters consume a lot of energy. In Luleå, we've got Facebook that is 120 megawatts, but then we've got a lot of megawatts in Boden, and we've got a lot of megawatts around the globe. What does it mean to make, to warm up some air and to throw it into the environment? It means to waste energy. We wouldn't like to waste energy, we would like to reuse the energy. And we would like to reuse the energy from the data center. And the more we warm this up, the more we can reuse the energy. You see what I mean? So, what shall we do with all this heat that we are doing? And how shall we reuse the heat from a data center? This is the stuff that we are working right now, heat recovery. Because from a societal point of view, recovering this heat means to have to use less energy production in the nuclear power plants, for example, to do the same things that we are doing right now. And important is that to see that there's two different technologies of servers. The first one is air-cooled servers. That is computers like this one. Computers for which you've got air that passes through. And then there's the next generation that is liquid-cooled servers, for which you have liquid. I do not know if it is sufficiently big, but basically this is those are pipes on which liquid passes, and the liquid goes then over the CPU, and it cools down the CPU, and then goes to the memories and cools the memories. And then what happens? It happens that air is much less efficient in cooling down the stuff. So air here, whenever we do air-cooled server, we got a temperature in inlet that is 15 degrees, and a temperature in outlet of the air that is 25, 30 degrees. Liquid-cooled servers, we can inject 40 degrees inside 40, and then we get outside 60 degrees. And that 60 degrees, we can directly throw them inside our local heating system. But I will talk about it right now. Because we've got to see that there's two main possibilities. And what I'm trying to convey now, the message that I'm trying to convey is, we understood as a scientific community and as a society that we should reuse this heat. How can we reuse it? What is the most meaningful way of reusing it? And we've got to consider there's two different types of reusing this heat. The first is locally. That means I've got a data center, and connected to the data center, I do something that I can reuse it. For example, a swimming pool. We like swimming pools. Warm swimming pools in winter here, they are very nice. We can grow greenhouses, and I will talk a little bit about this. We can heat our offices or our homes. Or something that is more intelligent and flexible is we connect the data center to the district heating network. Because the district heating network brings the energy, the thermal energy around. And then we let somehow the district heating manage where to bring the heat in an optimal way. And something that we are working right now is this kind of crazy idea, but I really like a little bit maybe. It's not completely out of the box, but it's something that has got a lot of meanings. It's a project where we are working right now that is called the Green Power, and is in cooperation with SLU in Umeå. That is, considering this branch here, okay, this branch here, instead of growing tomatoes or gurka. How is gurka in English? But I don't know. You understood? Let's do mushrooms. Why mushrooms? Because basically mushrooms, they require less heat. So 8 degrees are fine for mushrooms. They got a very high density of production of food in terms of land. So in a smaller environment, you can produce much more. And there's something that I really do not know. You can use them in pharmaceutical things and also for bioconversion processes. But also mushrooms, they reuse local forests residuals. And here in Luleå, especially, we have forestry. So it's kind of, and then the nice thing is that with the waste from the mushrooms, you can burn the waste from the mushrooms and then get energy also from there. So you would have like the data center that feeds the mushroom house that is fed by forest residuals that produces some fuel that you can produce ethanol. And then you can also burn the other stuff. So it's kind of a whole cycle. This Green Power, of course, project doesn't do everything, but somehow we are working on some sub-parts of this. And it's something that we are going to do. Also because there's one of the participants is a Chinese professor in SLU that has got a very big expertise on mushrooms, and he has been growing mushrooms also. And this is, for example, a picture on the test bed that we have in Umeå, where we are growing mushrooms with the heat, simulated heat from a data center anyway. And it's kind of a nice idea, the one of instead of throwing away the heat, reusing it for something that then we can also eat. Heat and eat, maybe I'm making a mess. And I've got also to notice that there's already some other places, Stockholm for example, where they are reusing heat from data centers. There's this open district heating Fortum, where they basically can connect, you can connect your data center, but any type of source of heat to the district heating network. And then the district heating network pays you a little bit for the heat that you're injecting. It's not very efficient, actually, because all the various data centers that they are using right now in this initiative here, they are air-based data centers. What it means that they produce air at 25, 30 degrees. And then they've got to go up to 65 degrees to inject the heat into the district heating. How do they top this temperature? Through heat pumps. Heat pumps consume energy, consume electricity. So right now, since we do not have liquid cooling, there's this using the heat pumps that is introducing inefficiencies. And this means that this open district heating, it's successful, but not as successful it would be with liquid cooling. But as a society, we are moving there. There's a lot of economical strives that are pushing towards the liquid cooling. And that will enable a lot of things. Okay, so some few words about how the future will look like. I think that this is the biggest vision that we have in the society, in the community, I would say. That is that data centers will be bridges between the electrical and the thermal grids. In which sense? In the sense that now the electrical grid is one electrical grid in the whole world eventually. So the whole world is connected with the electrical grid. So there's one whole electrical grid, but there's several district heating networks. For example, Luleå is not connected to Umeå. They are independent. But what happens? It happens that there's data centers that are connected through internet. Data centers consume energy, electrical energy, but they can produce heat, as we are saying. So the idea is that somehow, if the electricity, imagine that this is Norrbotten and this is Småland, okay? And then in Norrbotten we've got an excess of electricity, while in Småland we've got a deficit of heat. Then theoretically, if we've got a lot of data centers, what we can play, and this is like the big vision, we can make data centers somehow transform the electricity into information and process the information where it's needed, but not just from an IT point of view, because the IT traces, we can send them back, where the heat is needed and where the electricity is cheapest. So somehow, data centers might work as ways of moving around heat. Through exchanging information. And this is amazing from a technological point of view, because we would have a whole country, a whole continent, a whole world where we do not exchange just electricity, and exchanging electricity is a little bit costly. We exchange also heat through information. And we optimize the energy consumptions and the heat production all over the world. Maybe it's better if to say Sweden, because it's a little too big vision. Anyway, so there are some research directions, and the research directions are towards operation and maintenance and reducing the environmental footprint. There's a lot of things from a, how do you say, research perspectives that can be said in what to do. We can use machine learning and robotics to make the operation and maintenance inside the data center better. We can improve the environmental footprint by doing heat recovery, by doing interactions with electrical grid, doing this geographical coordination that we want, that we were saying before. But somehow, what do we need? We are doing some research over here. I don't want to enter into the details because they might be boring. Something that is important to notice is that we've got something that is very nice in Luleå. It's unique in the world, actually. This is a 6-ice testbed. That is basically a data center that we can use just for research purposes. We can do experiments. We can do whatever we want. This is paid by taxpayers, so thank you, taxpayers. But we can do a lot of experiments trying to improve the situation right now. And it's here, where there was a ferroform, if you didn't see it before, actually. So it's very close to the university. And it has got, it's not so big, so it will be eventually 2 megawatts, but it's big enough to do very big experiments. And somehow we will have to, the more we use it for experiments, the more we have to pay with some in-kinds. Of course, it's correct. It's not that if you use something, you should also pay. Anyway, concluding, data centers are huge and will be even more huge. And we need to do something for tackling the complexity and reusing the energy that they are consuming. This is a societal need. Throwing away gigawatts of power into the air has no sense, especially now that we have these type of energetical problems. But to do this heat reusage, we need to handle the energy flows. And this needs control. We need to know how to do things with machines, not with humans that poke around various valves. And with this, I thank you for the possibility, and I hope you like the presentation. And if you've got questions, please.
Thank you, Damiano. That was an amazing presentation.
Thank you.
Thoroughly and pedagogically, you took us through this field.
Thank you.
Are there any questions out in the audience? No? What's your next step? Where do you take it from here? What do you want to do?
There's the smallest steps are kind of some technical details around this kind of control here. These single servers control, this is like the smallest steps, but maybe they are not interesting. I think that the more interesting stuff is the biggest steps that are both this one, how to coordinate with the district heating, how to coordinate with the district heating in a way that you will fix things better, where you can reuse the heat in an optimal way. But actually the biggest step, and also the mushrooms production, this is something that I really like. It's something that I feel like, yes, we should grow mushrooms. maybe because I like more nature than computers. Yeah. But somehow this is the biggest vision. This is not the next step, but in 3-4 steps. I think that making data centers coordinate among themselves with the electrical grid and with a network of district heating, this is the goal. How to do it? Before, we need to understand locally how to operate in a better way. We need to understand locally how to operate with the local district heating, not considering the electrical grid. Then we need to consider the district heating network connected to the data center and the part of the electrical grid that somehow belongs to that zone. And then, whenever we got this, we can go towards the whole picture. So I think that the steps are like this, then this plus this, then this plus this plus this, and then the whole picture.
It's a never-ending story.
No, it's a never-ending story, yes. But here we are talking about energy systems. Yeah. Here is basically the biggest and most complex infrastructure that humans built. Yeah. It's if you think that you've got electricity and heat coming to every house, every building, and now you got you do not have humans controlling them, but you get algorithms controlling them. The level of complexity of these type of systems is unbearable for a single human. It's so it takes time, but at the same time, being so huge, if you improve a little bit, you improve a lot. So historically, we had electrical grid and district heating. It's like 10 years, 20 years, 30 years that we have internet. From a science point of view, we are now thinking how to integrate this information exchange with electricity exchange and heat exchange. It's the next step, I think. One of the various steps of humanity.
Yeah, really. Yeah. You know, I think, I know that at Oxford University, they have a chair, a professorship in public understanding of science. I think Richard Dawkins is one of them, very well-known former professors there. I think you could hold that chair because this was an excellent
Thank you.
presentation of an extremely difficult question. Difficult but extremely important question.
Yes.
Yes.
Absolutely.
Thank you for taking the time.
Thank
you for making the effort.
Thank
It was a pleasure to have you here.
Thank you so much. Thank you. Tusen tack.